We are ECGR 4101, 5101, ELET 4133. Is it 43 or 33 or 23? 33, all right. And this is lecture number 9. What I'm going to do is I'm going to go over quickly the solution to the exam, just to let you know that it is really easy. Here we go. And no, unfortunately, your name is not worth any points, all right? What is the range of decimal numbers that can be represented by 16 bits as 2's complement signed integer? All right, basically regular signed integer, 16 bits. And remember we said the formula was -2 to the n to 2 to the n minus 1, sorry, to 2 to the n minus 1 minus 1, correct? So all you really have to tell me is 2 to the 15 to 2 to the 15 minus 1. I would accept that. And if you did it all the way out, that's fine too. What is the range of decimal numbers that can be represented by 8 bits as a character? 8 bits is a valid size of a number that you could use. It's unsigned, right? So it's 0 to roughly 2 to the n minus 1. So it's going to be 0 to 2 to the 8 minus 1. But that's easy because that's 0 to 255. Well, that says range. Single number is not a range, right? And then finally, we did this. I did several examples. You did one yourself. This is fairly easy. What is 32? What's the representation of that? 1 and 5 zeros. Sorry, I saw you did 16. I hate when that happens, don't you? And this is, the decimal part is really easy, right? 1/2 plus 1/4. So obviously what we need to do is move this over 1, 2, 3, 4, 5 places. So our sign, by the way, is going to be negative, so that's going to be 1. Our exponent is going to be equal to 127 plus 1, 2, 3, 4, 5. So our exponent is going to be 1, 0, 0, 0, 1, 0, 0, 0. Oops. I got too excited there. And then our mantissa, remember this is assumed, so it is 1, 2, 3, 4, 5. Zeros followed by 1, 1, 0, and then followed by a whole bunch of zeros. How many zeros? 23. So our final answer that I was looking for is 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. All right, so I just did this quiz in what? 2 minutes. And I talked. And if I didn't show it to all of you, I would have gotten -1. So, you think you're going to see something like this on a test later on? Nope. Ah, yeah. So, again, ECGR, 4101, 5101, all right, I want pure honesty here. How many of you actually read chapter number 4? Raise your hand high. All right. How many of you are in chapter number 5? So it doesn't look like there's any difference for me covering what's in chapter 5 or chapter 4. So my preference is to cover chapter 5. So rather than what I told you that I would be doing chapter 4 today, I tell you what, I'm going to do chapter 5. I like software engineering, and we're going to look at that. One thing I do have to tell you is that our next lecture, which is, of course, Monday, will be chapter number 4, and it is almost assured that I will give a quiz on something inside of chapter 4. It is almost assured. And you know what? I'll probably put something on there on chapter 5 as well. So I would recommend you spend the time over the weekend. Let's see, what do we have in chapter 4? How many pages is that? Chapter 4 is, chapter 4 is kind of long. Between chapter 4 and chapter 5, it's about 8 pages. But it's light reading, it's fun, it's exciting. I need you to read it so that when I cover it in class, actually chapter 4 is mostly hey, look at, this is how one goes about developing code and such. So, or using our, what do you call it today? Our compiler. So, it should be fairly easy. All right, so, one thing I also need to point out is that I finally got up there the assignment for homework number 3, so it is due on Monday. Homework 3 is a really tough one. That's sarcasm. I'm going to make sure this works. Write pseudocode, write C code. What is the, and then a couple of questions about things that we covered in the last class, as well as some other stuff from book chapter 3. So, this should take you no more than an hour. Yes, sir?
Did you fix the Moodle?
Moodle is not fixed yet. So Moodle will be fixed when I get back to my office. Or I can do it right now as we sit here. So what I'm going to talk about today is hardware, software, co-design, and general concepts associated with software engineering. So how many of you have actually taken a software engineering class before? That's what I thought. And so this is going to be a somewhat new yet abbreviated discussion of how they develop software in the real world. Pardon me? Parallel. Oh, concurrently. Yeah, as I said, hardware, software, co-design. In other words, how are you going to do your software while at the same time they're designing hardware? So let me start this off with a motivation. When I was working on a mobile phone project, we were literally starting from scratch, designing the hardware for a phone. And so I can give you the example. From Qualcomm, we grabbed a chip, and if I remember the chip, it was their, I'll just call it the 5100 series, which was a CDMA 2000 chip. And when they say chip, it means that on this chip was a microcontroller and a digital signal processor. That's pretty neat. Microcontroller was ARM7 based, I believe. And this was in 1999 when we started this work. So I date myself. So, but anyhow, it's the same concept. So we knew which chip we were using. And I don't know about you, but you really can't go out there and buy too many evaluation boards where you have a digital signal processing chip and a microcontroller all rolled together on a board that has lots of I/O. They actually kind of have one. Their development board for this was 2 feet by 2 feet. Oops, not inches, 2 feet by 2 feet. And it had some chips on it, and what I really loved is it had a really old style telephone handset, you know, with the microphone and, you know, a wired phone. Have you ever seen one of those? Just wondering if you have, you know. So and a wired handset, and that was your development environment for this. And so, if that's all you have, how do you develop software at the same time that they're going to make a phone, where really the goal is to make a board? In this case, it was approximately 6 inches by 2 inches. So don't forget, this is a system on a chip. So what it turns out is that when you first start doing hardware and software co-design, you really have to rely on general concepts of I can get a lot of this stuff going in things like this, I can get a lot of code going in an emulator, but at some point in time you have to pull it together. So you have to imagine, we're working with a system. I believe we've talked about systems already, right? Was it this class or am I thinking of another one? Okay, nobody's answering, yes, no. Haven't I talked about requirements and design and, oh man, was this another class? I know it's robotics, but I thought I had actually started in this one. All right, well, I guess I need to start with from the scratch here. So let's step back and say, well, we're going to develop a system, and the system has many parts. What comprises a system in general? Let's take, I didn't bring my mobile phone, so what did you say? All right, we have hardware. What kind of hardware? All right, so electrical hardware. Software, electrical hardware is part of that. What else? We're talking about a mobile phone. What else do you think is involved?
My case.
All right, case. So that's mechanics. So we're going to say software. We're going to say the base, operating, and communication software, right? Because to distinguish it from anything else. Anything else? When you buy a phone, what do you get? See this over here?
Power supply.
Oh, you get power supply. Paperwork. That's a system. Everything comes in the box. You're missing one big thing. Oh, okay. You're missing two big things.
Earphones.
The what?
Earphones.
Oh, earbuds, all right. Power supply. I think I heard it, battery. So that represents the box that you get and everything in it, right? But if we're talking about the whole process of developing a mobile phone, we're missing something, right? Yeah, some of the stuff you're missing is the people. You're missing testing. You're missing the whole concept of manufacturing, delivery. So when we're talking about a system, and this might be a little bit more apparent if you're talking about a huge system like the space shuttle. You know, the space shuttle has software in it. It has electrical hardware. It has mechanics, avionics. Then that's attached to a fuel tank and the side boosters. But then that's not it. That has to sit on a launch pad, and it has to have communications with the outside world, like with satellites and sending stuff down to Earth. So there's a whole, and then there's all the people that run mission control, etc. So when you're thinking about a system, and you're thinking about an embedded system, you have to think about everything that's added up together. So what I'm going to suggest or take a look at is that how are we going to decompose everything? And so there's some general concepts associated with decomposing a problem. And so I'll just take a look at, or point this one out. So first, this is just a funny little projector. It kind of squishes everything. Or does it show squished up there? Maybe it's just me. So eventually somebody has to come up with the need. What is the need for our entire product and project? Somebody's going to work on the development of that. And then the product design is going to happen at about the same time as the manufacturing design. Then you go into full production and deployment, support, maintenance, upgrades, retirement, disposal. So all of those are different phases of an entire embedded system, or a product associated with an embedded system. And of course, the ones that almost all of you are going to be excited about are the ones right here, product design. Get your hands on it. But in the end, where you're probably going to have the most value add, that being students that are well-versed in electrical and computer engineering, that have advanced degrees, perhaps even masters in addition to your bachelor's. I'm assuming that all the people here getting bachelor's degrees are probably going to get a master's degree too. Even the engineering technology students, I got tons of master's students who are former ELETs. So if you haven't met them before, in fact, we've got one of them here. Who was that? I was talking to you the other day. All right? Former ELET. So he knows that it's going to take a master's to get a good, really good job. And for those of you who are getting bachelor's in electrical and computer engineering, you might want to consider that too. Anyhow, where you're probably going to have your big value add is during the need opportunity concept development at the beginning of product design. Because to be honest with you, there are too many people out there in the world, in other countries, India, Vietnam, China, Malaysia, that are very good at production and a lot cheaper than we are here, that in some respects can do a pretty good job in writing code. And they're a lot cheaper than you are here. So a lot of your value add is going to be at the front. So don't go thinking you're going to be a code monkey here in the U.S. because there are very few true code monkeys here in the U.S. So what you're really going to be interested in is not only the need opportunity concept development, but controlling the product design. So you'll be able to have your co-ops, your bachelor students start working on that. So if you look further at an entire life cycle in hardware and software co-design, you will have something very similar to this. Specifically, you're going to have a concept where you will have to create requirements. And can everybody see this well? This is one of the that looks a little bit better. This is one of the pictures from the book. And think about this. How do you know what you're going to build? How do you know when you're done? Say that again? All right, when you have the functionality. So have you determined what the functionality is? So I guess the big thing up front that you need to think about is to ask the question, how do you know when you are done? And the answer is when you have finished. for somebody to, Josh, at least you could say something. Oh, you've already been through this lecture already, so you know what this is.
When you meet the requirements.
All right, when you meet the requirements. So, what you have to do is you say, you have to define what you must do is equal to the requirements. The requirements say things like, this phone will be CDMA 2000 compliant. This phone will weigh less than 5 ounces. This phone will have an average life of 3 days while delivering 1 hour of talk time. This phone will come in black, red, and blue. These are the types of things that you could include in one's requirements. Sometimes they go so far as to say, I also am going to make requirements on maybe screen resolution. So you can say, e.g., color, weight, performance, screen resolution. So in addition to that, you are identifying how you're going to test it in the end. So at this point, one thing that you can ask is, well, the first thing I do is I pretty much identify my requirements, some general requirements, and then I'm going to write some specifications, some specific sentences to address what I'm going to cover with these requirements. And typically what happens concurrently is another group identifies how they're going to test that. So they're going to say, well, I need to develop a test plan, and this test plan will tell me how I can test, validate the requirements. Once all the requirements are identified, a systems engineer will help identify who gets what pieces of the requirements, and then they'll start to do their basic architecture and design. So at this point then, the architectural design is going to go on where the software will get all the software requirements over here. Oh yeah, I must be able to operate at a certain number of instructions per second. I will have to ensure that I fit in 3264 megabytes for the basic operating system, etc., etc. Hardware will get the requirements. I must run a screen with resolution of 1000 by 1000 with a certain number of pixel pitch and certain number or a certain amount of refresh rate. And then once you define, and then the mechanical will get, everything must fit in a 6-inch by 3-inch space, and the case must be metal and come out, be made of aluminum. So at the same time the architecture is designed, you have another group over here, which is looking at more test plans. The test plans are how are all those pieces, in other words, how are the computer or the software pieces and hardware pieces going to be pulled together, and then validate them. Now, as you can imagine, sometimes you need to work with the hardware and software separately. And once they're working separately, then you can bring them together. Remember that example I showed you earlier? This test station? So this was a test development board. Does it look like this development board over here had a a nice small form factor? No. But it had the functionality that you'd be able to test your software. So in the same way that you have to develop and implement separately, you'll have to then design separately based on the architecture. And now you're going to be working on the detailed design. The hardware groups and the software groups will start to work a little bit separately. In a good group, they'll talk to each other. Then the test group will also identify some more test plans on how they'll pull everything together and test it as they go through. And then, of course, then comes this says coding, but in the world of embedded systems, that also includes hardware development as well, hardware design, algorithm design. At the result of all of this, you will have code, and this will be prototyping. And then on the way up, the software group will take the hardware, and the first thing they'll do is unit testing. And that will be a small part of, or I should say, they'll work with small pieces of code, and they may also work with small pieces of hardware. This is called the V model of development. So, as a form of getting you to think about something, I want you to do and turn with your neighbor and identify the following. This will even help maybe for a future lab assignment. You never know. I'm going to develop the following product. My following product will do this functionality. I will have a device. It will be 1 inch by 1 inch. It will attach to the wall with Velcro. It will have a 3-volt watch battery. It will have the following functionality. It will measure the temperature and humidity every 1 minute. And record the following, or I should say, and transmit. One. This is from base station 1. This is from base station 2. Temp in Celsius, and the humidity. And I'm even going to go so far as to tell you what this will be, is in tenths of C. For example, 20 degrees C will equal to the number 200. Humidity will be in 0 to 100. Hey, can we have more than 100% humidity? I don't think so, right? All right, so I have a product. Looks interesting, right? So what I would like you to do is the following. I'm going to have you do a simple system. And I'd like to have 3 of you do this at a time. So that you can give me a nice answer. I'll give you 10 minutes for this. And you know what? I'd like to have some diversity. So if you're an ET student, sit next to somebody who's not an ET student. If you're a CPE, sit something who's next to somebody who's not a CPE. If you're a grad student, sit next to somebody who's not a grad student. I think we have more grad students here than anything else, so you might have to double up. So your goal is the following. Define what is important for each of the following subsystems. One will be mechanical. Next will be electrical hardware. Next will be software. So, should I solve one of these, like for mechanical, as an example? So let's see, we have this example system. And if I were to look at this device, well, I know in my mechanical, I'm going to have a subsystem of this, which is going to consist of the case, Velcro attachment, right? Let's see, what else do we have to worry about for the case? It's a small little box. It's Velcro. What else do I need to worry about? Oh, what is Velcro? You know, Velcro is that what they call something and hook. What is it? Cloth and hook, or that's Velcro, right? This is Velcro. Velcro is actually a trade name for this where. Notice I put my attachment here and it holds pretty good and pulls apart. All of you know what Velcro is, right? You just never heard that name. So what's the Indian name for that? Velcro as well. Okay, what's the Chinese name for this? Velcro. All right, let's go on. All right, what else is part of our mechanical? We have an outside case. We have Velcro attachment. What do you think?
Heat. Like if it heats up, it should go outside the system, right? So
Yeah, but that's probably part of the case. If you're looking for heat and you're looking for it to measure something, that means you need to make sure to put something in there, right? A what? An antenna? I'm going to say we'll make that part of electrical. All right. You want me to do one more as an example? I'll do electrical, what the heck. So as electrical, it's going to be the microcontroller. Sensors. Looks like I'm just solving this problem now anyhow. It's not going to break up, right? PCB, no display. Let's see, we need read all the requirements? I said, distance from base station, 10, microcontroller, oh, look at that. Transmitter. I don't say anything about actually receiving anything, do I? Well, I'll say it's part of the transmitter and receiver. No LCD, I want to make this really cheap. Notice I never said anything about here about an LCD, all right? Transmit the following. So, now what's left is software. So as a part of your software design, what you need to start looking at is, oh, look at that. Distance from base station 1, distance from base station 2. How do you determine that? How many of you are taking any communications course right now? Raise your hand high. All right. Has anybody ever heard of the word RSSI?
Receive signal strength stability.
All right. Receive signal strength indicator. All right. Anybody who knows that, you need to be in a group with somebody else who doesn't know that. Temp, humidity, every minute. So I'll give you, since I did half of it already, I'll give you 5 minutes to write down something similar to this of the pieces of software you have to worry about. Go to it. All right, so we are back, and you've got a chance to think about this, and there are several parts of the software design that you need to worry about. So let's look over here, software. So, what's one thing that we need to take care of?
Memory and data.
Say it again?
Memory, how we take in the sensor data and put it in the memory.
All right. Store data. What else?
Communications.
Well, baud rate's part of communication. You have to keep track of timing. By the way, an ADC, analog to digital converter, is that software or hardware?
Hardware.
All right.
Error
And
handling.
is that represented by microcontroller? All right, so you need to have sensing.
Error handling.
And error handling. And probably one big one that everybody's missed so far.
Computation actually.
All right, the distance computation, right? And even though it's not in here, it is implied that there's going to be overall operating system control. But to be honest with you, for something that's this simple, you probably don't need a full-blown operating system. You can get by with what we call a roll your own, or really just a super loop. In other words, just do a few things and go on. In other words, you don't need to have, most likely you don't need to have anything like garbage collection and stack overflow identification, because this is going to do only a few things. This thing is going to record and send, and maybe, although at the beginning, identify the distance that you are. For those of you not familiar with distance computation, imagine I put a base station here, which is also not in the requirements, So I put a base station here, and then I'll put one over on the other side of the room, and a radio, any sitting anywhere in this room can listen. And based on the strength of the signal from this one sent out and that one sent out, you can have a pretty good guess about how far away you are. You can get true identification or triangulation with 3. So if I put one here, a base station here, one over there, and one up there, and all it did is it sent out a beacon saying, hi, hi. You can tell based on the strength, assuming that all of them are consistent, about how far you are, right? Well, how could that be? This is a side note. So based on my communications, if it looks that I have a certain signal and it's with this diameter here of the signal, and I have another one and it's about this diameter of the signal, technically speaking, they cross here and here, and then based on this, I'll be able to determine that I'm really over here. Triangulation. Do I worry about this now? No. All right, just wanted to give you that idea. Now, I'm going to change gears a little bit and have another problem, which is discussed in the book. And that is the co-author of the book, Alex Dean. He likes to sail. In fact, he has a beach house at the beach, and he likes to sail in the Sound, Albemarle Sound, I think. I'm not positive. And those of you who like the water and stuff like that. Anybody who's been to the coast of North Carolina in the Sound? All right, just a couple of you. Wow. All right. So let me identify the problem. And I'm going to put this in the notes so you'll be able to look at that as well. So Alex Dean, he likes to sail. The only problem is that in the Sound, which is the area of water between the outer islands, or what they call the Outer Bank, and the mainland, the depth varies greatly. It could be as deep as 40 feet, it could be as shallow as 0 feet. It could be a little outcropping of rock or something like that. And so if he's going along, and he's got this sailboat which has a central part here called a keel, right? Nobody here sails? All right. There's a keel here that keeps a sailboat from going sideways. It keeps it going straight. So he doesn't want to scrape this on the rocks that might occur. Man, you guys are learning so much in this class, aren't you? The field trip out to the how about that? So there's this big area. This is the coast of North Carolina, these little islands here. And in here, in the Sound, is where he likes to sail. He doesn't want to run aground. In other words, he doesn't want to hit rocks because that's really bad for the bottom of a boat, all right? As well as this keel that sticks down about ½ a meter into the water. So, what he wants to do is he wants to map the water in the Sound so that he, with using GPS and a depth meter of some sort, so you can identify the depth of the water. And if you're familiar with oceans, you'll know that there's such a thing called a tide. And so when it is high tide, the water comes rushing in from the ocean into the Sound, and it raises the level of water in the Sound. And that's because of the gravitation of the moon and the sun at the same time, makes it so that the sea level will actually rise. You all know about tides, right? Okay. So I'm not saying anything new. Interesting enough, that's what riptides are formed by, water rushing into the Sounds. And then at some point when it becomes low tide, it all rushes back out. And that's what riptides are, they pull you out to the ocean. So sound, the best time to actually do the measurement of this would be at what, high tide or low tide? Okay, who votes high tide? Who votes low tide? Who votes it doesn't matter? All right. I would probably want to do high tide. Why was that? Why would that be? That's your best case, right? In fact, that best case will tell you at some point, oh yeah, there is water here so I can travel. And, oh, by the way, if there's something right below me, I know it's going to be rock later. Or, better yet, there may be some areas at high tide that are 1 meter deep, that at low tide is 6 inches, or that would be half, or about 100, not 100, would be like 10 centimeters deep. So it would be better to do it at high tide because you have a better chance of not scraping bottom as you measure. And then, of course, later on, you probably have to adjust for tides, right? You'll have to say, oh, if I'm sailing now in low tide, just subtract 1 meter off of all of these measurements, as an example. So let's identify some other requirements. So I will write one of my requirements like this. Map the water so that with GPS you can identify the depth of the water. And then you would have to add other things, like the measurement will also record the current tide levels. So it would be good if I'm measuring at high tide, that I actually recognize that I am half a meter or an entire meter above normal sea level. And at the same time, of course, I can just show all these at one time. The location via GPS will be recorded every 1 second. And whatever you're recording this with, the embedded device will be fairly small and waterproof. Now, is this a software requirement right here? Not really. It's mechanical hardware and electrical hardware, but it's not software. Is this software? Yeah, that's pretty much going to be a software requirement. Is this going to be a software requirement? Yeah, well, you're going to have a computation. You're also going to have some GUI. Because how do you know what sea level is or when high tide is? So you're going to have some sort of input from the user. All right? This is a general function, or I should say a general capability. So let's look what else do we have. 12 volts or less and draw no more than 1 amp. Is that hardware, software? How's that hardware? Depth shall be measured with a OTS fish depth finder every 1 second. Hardware, software, or both. Kind of identify what you have to use as a depth sensor now. GPS and sonar shall communicate via RS-232C at 4,800 bits per second. Mostly software, right? Hardware, we're defining RS-232, which is a hardware interface. It's a hardware and software interface. Record the wind speed and direction. That's interesting. So again, you're going to need some hardware to be able to measure that phenomena, and the software is going to have to handle it. And the device shall have a minimum of 512K bytes of data flash. So again, that'll be another concept that will be worthwhile to understand how you're going to run. So, with that in mind, and this is also shown as a picture of 5.5 in your notes. So I'll just show this here. We have taken the liberty of decomposing our problem as such. We know that we're going to hook up a sonar. And our communications method with the sonar is going to be via a RS-232. We're also going to identify with the GPS RS-232. And as it turns out, we're going to need some software to be able to grab information from here whenever we need to grab the information from there. Now, you can set up these devices that will automatically transmit data every 1 second, every 5 seconds. So what you have to do is you have to actually have a method to set up this device, and then thereafter, and I think most of these you can do it with by hand. And then thereafter, it will send every 1 second the data. And in fact, the GPS is going to be the most accurate for sending stuff every 1 second. So you will need a piece of software, and we've designed it. We called it a UART, Universal Asynchronous Receiver Transmitter, Interrupt Service Routine. We're also going to set up a interrupt service routine for this global positioning system. So this is going to be 2 pieces of our software design that we need. We also need to, in the process, or in our machine, we're going to need to take this data that we receive and do some adjustment with it. Because I know from working with these devices that they send you a heck of a lot more of information than you really need. In my depth, I'm only interested in one number, depth. How much is there between here and there? It may provide me a lot more information, like maybe the temperature of the water, which for this application I don't care about. Maybe it might also have a device on it that tells me what the wind temperature, or I'm sorry, the wind speed, and the air temperature is. So let's see, did I want to, here's the wind, speed, and direction. So maybe it will record that as well, and I'll need that from there. The GPS will give you more data than you know what to do with. Has anybody actually seen a data stream from a GPS? And this is not just the screen, right? It will provide you all sorts of information associated with not only your latitude and longitude. It'll give you, let me just tell you, a whole lot more information than you need. So you'll need to actually process the data and store what you need. What's the current depth? What's the current latitude, longitude, current time, current date, current temperature, current, I can't even tell what that is. Velocity of the wind, and also we're going to store how much memory. This is a temporary storage. How much memory is being used from our special device over here, our flash data memory, which is going to hold every 1 second. It's going to hold whatever we're measuring. And then we're also going to need to print out and have a user interface. Now later on, when we get back home, we're actually going to add another special function to it. And it will be the ability to read this data from the flash and then bring it to a PC. Where on the PC, we'll take it and we'll do our modification for that. In other words, as you can imagine, we're going to go sailing. And are you going to travel that entire ocean or that entire water surface like a lawnmower? Back and forth and back and forth. No, you're going to be all over the place. And so you'll need to do some post-processing. So what I wanted to identify is that, yeah, there may be a need to split up our software into different components. And we're going to get into that in a lot more detail in some later chapters. If we look at one of these in a little bit of detail, we can get into what's called a detailed design of this. And as an example, we can look at a flow chart. So here's our design. We have a queue of data that comes in, and we need to decode it and work with it. Is it valid data? Yes or no? If it's not valid data, let's just leave. If it is yes valid data, then we will update our current position. And oh, by the way, is that an update from something previously? because if it hasn't changed, then we don't have to write it out. Or if, for example, you might be sitting in the same place and not moving. If you're sitting in the same place, you don't want to store, okay, I'm here now, I'm here again, I'm here again, I haven't moved, yeah, I'm here again. So they make sure that you actually move. And then you update your variable called memory used, and then you end. This is an example of a flow chart which has a description of the data that you might be saving. Yes? Oh, excuse me, not, I have a question, but I'm sneezing, okay? And again, you have already had an experience with implementation. And so we will just go on and assume that you know what's going on. So let's talk about testing really quick. If I want to test this entire system, there's two ways I can do this. Specifically, testing is in two realms. One is called black box, and one is called white box. As you can imagine, with black box, this is your device under test. And the problem is you have no idea what's going on inside. So the only way to test a black box system is to give it a set of input. And then for the output, you should know what is expected. And the hope is that what you put in will generate and go through the code correctly, that what you get out is exactly that. So if we look at our example here, we can test this right here, this software here, using a black box approach. We can give it a specific input and look to see what the output is with respect to position and if it changes the memory used. Now the other one is called white box. And white box works with the respect of you have input, and of course you have the same output. But you know if whatever you give on the input will generate something on the output. So I could specifically write test cases that I know will be the following. One test case could be invalid data. If I send invalid data in here, I know it will immediately exit and nothing will be written out. That would be one example of white box testing. I know that that's going to be one of the things I could give it. The next thing I could do is I could give it new data. And based on new data coming in, I'll know what the expectation of it coming out is. And then maybe the third thing that I could do, is I could just say old data. In other words, I'll give it one piece of data or one NEMA string, and then I'll send the same one in. And the expectation is that I'll exercise this path right here. And I will expect no changes for either of this if I do the same thing, same data as was previously there. Now, based on these three test cases, have I tested all the possible code paths here? It looks to be like I have, right? I have one code path which takes me immediately here. I have one that takes me here, and I have one that takes me all the way through. And that would be the example of white box testing. Finally, oh look at this, I've got 1 minute. This works out well. As you can imagine, developing an entire system is pretty tough. And so maybe I want to do a little bit of functionality at a time. And so that's something that we call spiral. In other words, we identify what we want to do. We'll do a little prototype evaluation of that. We'll build the product. We'll evaluate it. And then we'll think about what more functionality can we add. So maybe with this system that I showed you a little bit earlier, I would come up with, let me try and get the GPS working, only the GPS. So I would get the GPS working. It works fine. Now let me add the depth sensor. I got that working. Good. Now let me add something about the wind direction. I got that working. Good. Now let me add the concept of writing the data out. Got that done. Great. So what you're doing is you are working in a spiral, giving it more and more and more functionality as you go on. All right? With that, I am done. Read chapter 4. Thank you.